title of the section is Parameterized Surfaces and Surface Area. We're ultimately after surface integrals, but we need some warm-up. And to tell you the truth, the hardest part about this is understanding how to parameterize surfaces instead of parametric curves. But here's the key insight. You can think about parameterized surfaces as being made up of unions of parametric curves. Take a bunch of different parametric curves and like stitch them together. And that gives you a parametric surface. But you do need two parameters. We end up calling them U and V instead of one parameter, T. But here we do have in number 3, we got a surface. Z equals a function of X and Y. The function happens to be 3x squared Y. You already know that that equation has a graph that's a surface. What does the surface look like? I probably dare not draw it, but just looking at the equation, I could say like for any fixed Y, okay, imagine an x-axis coming towards you and a y-axis going this way and a z-axis going this way. For any fixed Y along a plane like this, the graph's going to be like a parabola because it's 3x squared times a constant. When Y is positive, it's an upward opening parabola. When Y is negative over here, it's a downward opening parabola. So I guess imagine stitching together a bunch of parabolas that are like this. When Y is 0, it's a horizontal line. And when Y is positive, its parabola is opening up like this, giving you some surface. That's what the surface very quickly in my mind looks like. Okay, the directions say parameterize the surface over different regions. Part A, we over a rectangle bounded by X going between -1 and 1 and Y going between 0 and 2. Part A, the rectangle R, we could use set builder notation if we like, and write it as the set of points XY, where X goes between -1 and 1, and Y goes between 0 and 2. Parameterizing it over a rectangle is fairly easy. It gets harder when it's not a rectangle. What we're after is a little r function, vector function, of, again, 2 parameters, call them U and V, instead of 1 parameter T. This is a surface, not a curve. And the standard way to do it here is to make the first component of your vector U, the second component V, and the third component F of UV. If you are parameterizing over a rectangle. This is the standard way to do it when you are parameterizing over a rectangle. Effectively, i.e., X equals U, Y equals V, Z equals F of UV. But we do want to use, it's not that we couldn't still just use X and Y as our parameters. We could write XY, F of XY if we wanted to. However, it's going to be more useful to use other letters. Just a little easier to think about when we're not parameterizing over rectangles. Okay, we'll see why as we get to those examples. As far as understanding how to graph this, there are 2 ways to graph it. Let's define the function here first. I guess I will graph it with plot 3D. Plot 3D will graph the function in the usual way. And we can plot it over a rectangle. X goes from -1 to 1, and Y goes from 0 to 2. And get a graph. And actually, yeah, the positive x-axis, I'll remind you, goes to the right here. Positive y-axis goes into the screen. When Y is positive, you do see you have upward opening parabolas. When Y is negative, well, I guess it doesn't go negative here, does it? If I did allow Y to go negative, then we'd see downward opening parabolas. But Y is not going negative. it might be good for us to plot this over a window that's a bit bigger. So we see this as a piece of a bigger surface. Like if I put a plot range in here, -3 to 3 for X, -3 to 3 for Y. And how high does the graph go? It looks like it goes up to 6 or so. Oh, I don't know, -2 to 10 for Z. We see it as a piece of some bigger unseen surface. And we could also, in fact, plot the zero function, a horizontal plane at Z equals 0, over the same domain and see sort of the underside of this graph, if we wanted to, so to speak. Yeah, when Y is positive, it doesn't go below that, but it gets very close to that plane there as well. But here's a new way to plot this. Define R of UV as a vector. I think for purposes of graphing in Mathematica, it will be best in general to think of the input as two-dimensional and use curly braces like this. That would, for example, allow us to plug points into it. But this is going to be a vector written as a list in Mathematica. And technically speaking, if we want to plot this as a parametric surface, instead of using plot 3D with this function R, we'd want to use parametric plot 3D. And if you use curly braces when you define it, you need to use curly braces here as well. X equals U, so U goes between -1 and 1. Y equals V, so V goes between 0 and 2. And we're going to get the exact same surface, though it may pick a funny window. Yeah, it did kind of pick a funny window and a funny way to choose the scales. I think it made the scales better in a sense. It made them more accurate. It made them the same in each direction here. If we decide to include the plot range option here, which is probably a very similar picture as the other one, except that the scale's a little different. I think I actually looked up box ratios is the 1, 1, 0.4 will make it the standard picture. There, yeah, if you compare these two pictures, they pretty much look the same, except I didn't do the one on the bottom. So it is parameterizing the same surface. Can we think of it in terms of vectors? I wrote this thing as a vector. Can we think of it in terms of arrows? Yeah, you can. Let's give this plot a name, call it plot 1. I could show that plot 1, with an arrow, or maybe even a bunch of arrows. Use graphics 3D to make arrows, individual arrows, not vector fields. Maybe thickness, 0.01, red. Arrowheads can make the arrows easier to see. 0.1, I think might work. Arrow. Start at the origin, 0, 0, 0, and go out to some point R of that point. U equals, I don't know, 1, V equals 1. Okay. That's drawing an arrow from the origin to one of the points on the surface. If I change the point, if I change the input for U and V, then I change the point that it's pointing to. There's another example. You can imagine doing that for all inputs U and V, where U and V range over between -1 and 1 and 0 and 2. And it's like the arrow will trace out the surface. By the way, you can get parametric curves from this too. And here's how you can piece these together using parametric curves. If you fix one of these variables and let the other one vary, then you get a parametric curve. So for example, if I set, Y equals 1, if V is set to 1, then I get a parametric curve in U. U comma 1 comma F of U1 is a parametric curve in the 1 parameter U I could plot that as well with parametric plot 3D. R of u comma 1 as u varies from say -1 to 1. Let's make it stand out. Plot style, thickness, blue. That one curve that you see there is one piece of the surface. If I now allow this one to change to be something else, I could put it in a maybe I should go ahead and do that. Put this in a manipulate where I've got a parameter representing v that's changing from 0 to 2 and make the 1 a v. Now I can change v and get a bunch of different parametric curves that altogether generate the surface. I could also do it the other way around and fix u and let v vary, and I get other curves that go into the screen. But now it gets harder. Part B, parameterize it over a circle of radius 3 centered at 1, 2. Effectively, what I'm trying to parameterize with part B, I could make with my plot 3D by including the region function option. Function XYZ, comma, what am I trying to do here? I'm trying to plot it over a circle of radius 3 centered at, actually it's centered at 1, 2. I guess I'm going to need a different plot range here. Circle of radius 3 centered at 1, 2. Let's see. That inequality? Circle of radius 3 centered at 1, 2. X minus 1 squared plus y minus 2 squared equals 9 would be a circle of radius 3 centered at 1, 2. By making it less than or equal to 9, then I've got the disk inside the circle. I better make this bigger though. Go back to bigger. Okay, that's sort of better. We need more plot range in the vertical direction. I don't know, -20 to 20 or something. Getting close. So the surface is this Pringles kind of shape thing. Getting close to seeing all of it. That's the surface. It is over a disk of radius 3 centered at 1, 2. That's the surface we're trying to parameterize. We haven't done it yet. We just use plot 3D to make this, not a parametric, not a parameterization. How do you come up with the parameterization? BR is the set of points XY satisfying the condition x squared plus x minus y squared plus y minus 2 squared is less than or equal to 9. Picture-wise, disk of radius 3 centered at 1, 2. Something about like this. We're trying to parameterize the surface over that disk. How do you do it? It's helpful to first parameterize the outer circle, the boundary. We could parameterize the circle, the boundary circle, with cosine and sine pretty easily. We could use, let's call this x and y. We could use x equals 3 cos u plus 1 and y equals 3 sine u plus 2. The 3 and I mean, I could have used a different letter besides u. I could have used a theta. The 3 cos u, 3 sine u would parameterize a circle centered of radius 3 centered at the origin as u goes from 0 to 2 pi. By adding 1 to x and adding 2 to y, we parameterized the circle centered at the point 1, 2. But that's only the boundary. How do we parameterize the entire disk, the boundary circle and what's inside? We can effectively scale the 3 cosine u and the 3 sine u by a v that varies between 0 and 1. Multiply those terms by v. For the disk, x and y are both going to be functions of u and v. This is not too dissimilar from the transformations that we did with the Jacobian matrix. We're just really getting more practice with coming up with formulas like this. If we take the terms, the 3 cos u and the 3 sine u, and multiply them by v, say, right, 3v cos u plus 1, and then 3v sine u plus 1. That should parameterize the entire disk. U goes between 0 and 2 pi. It's like an angle. V goes between 0 and 1. When V is 0 in these equations, you get the point 1, 2, no matter what U is. When V is 1, that's like this, you get the boundary circle. And when V is between 0 and 1, somewhere in between, you get intermediate circles. This is kind of similar to polar coordinates. V is similar to R and U is similar to theta. Once you've got X and Y in terms of U and V, then you can write Z in terms of U and V, because you can write Z of UV is F of, use the function, X of UV, comma, Y of UV. I'm abusing notation, somewhat common in this context to do so. I'm using X, Y, and Z both as variable names and as function names. But I do have a function that I'm calling F. I plug 3v cosine u plus 1 in for X and 3v sine u plus 1 for Y. Now, what was the formula for F? The formula for F of xy was 3x squared times y. So in the end, if I'm going to do this by hand, I'd have to do 3 times the x, which is this, squared times the y, which is this. I'd have to expand all this, and that would take a few minutes to do by hand. I'll get it started. I will go ahead and FOIL that thing and multiply it by itself. I am going to get a 3 squared is 9, but times another 3 is 27. V squared cos squared u. I will also get 3 times 1 is 3, but I'd have 2 of them from the outside and inside terms. I'm imagining foiling here in my mind, giving me a 6, but I also multiply that by 3 to get an 18. V cos u. 1 squared is 1 times 3 is 3. That would be the first step in trying to simplify this by hand. Then I would have to continue multiplying. Let's have Mathematica finish it. So I've got my function f entered. Let's just type it in. 3v cos u plus 1, comma, 3v sine u plus 1 into f. Expand. You can see it wrote down exactly what I wrote down by hand there. But expand that to simplify. There it is in all its craziness. You don't need to write that down. Question?
Should it be plus 2 or 3v sine?
Yeah, thank you. There are lots of mistakes then. Go back here. This should be a 2 here. Making this a 2. Making that a 2. And that a 2. Thank you. Change that in Mathematica too. No pun intended. Make it a 2 there. All right, there it is. You don't need to write that down unless you really want to really fast. Is that the final answer for the parameterization? No, we're not quite done yet. That's Z. We need X and Y. Well, we already wrote down X and Y. There they are. So with this example, the R of UV that parameterizes the surface over this disk, the first component is going to be 3V times cos U plus 1. The second component is going to be 3V times sine U plus 2. Don't make the same mistake. And the third component is going to be all this. Wow. That's the parameterization of the same surface as before, but now over the disk instead of the rectangle. Wow. Can parametric plot 3D plot it? Yeah. Give it a try. So this is my new R of UV. I do need to change the limits on U and V. U is the angular coordinate, so to speak. It goes from 0 to 2 pi. V scales out the circle to a circle of radius 3. The 3 is taken care of, by the way, with the 3's there, the radius. So V is not truly a radius. It's just a parameter that allows 3V to be the radius, effectively. I mean, I could change the 3's here and here and here to be 1's and then let V go from 0 to 3 instead of 0 to 1. I could do that. And what do we see? There it is. Oh, do notice though that Mathematica is drawing this in a different way. Back up here with plot 3D, it's drawing lines parallel to the X and Y axes. Down here, it's drawing like polar coordinates, radial lines and circles. It is the same surface. The book in this problem asks you to do more, to also parameterize it over a triangle and over a region bounded by the x-axis and the graph of equals 1 minus x squared. I do want to try to get to those things, but we also need to do something else. We need to find the surface area of these things with this formula. Number 3 doesn't ask you to do so, but let's do so anyway. There's two S's in here. One's kind of an ordinary S and one's kind of a fancier cursive kind of S almost. The ordinary looking S represents the surface area. The cursive-y kind of italicized S represents the surface itself. The surface area S of S is given abstractly as a double integral of ds. ds is a small element of surface area. S, the plain old S is supposed to represent a surface area. And the ds is a small element of surface area. And so in the abstract, we find the total surface area by adding up the little surface areas. But then as always, the question is, how do you actually do that? And you do it as a double integral over a certain rectangle. R is going to end up being a rectangle. For the parameterization of the surface that we just did a few minutes ago, the rectangle is U goes from 0 to 2 pi, V goes from 0 to 1, which you could draw in, say, a separate UV plane if you liked. Of what? The magnitude of the cross product of the derivative of R with respect to U with the derivative of R with respect to V. These subscripts mean derivatives. What in the world? Okay, we don't have time to explain why this works, but let me hint at it. You remember way back, first 3 weeks of class, sometime, we talked about dot products and cross products. And we said the magnitude of a cross product gives you the area of the parallelogram spanned by the vectors, two vectors, 3 dimensions. They span a parallelogram. What's the area of that? It was the magnitude of the cross product. You can verify it by trigonometry. That's related to this. Let's just say it that way. Effectively, this magnitude of that cross product is effectively magnifying areas of small rectangles. You got these rectangles. R itself is a rectangle, and if you could decompose it into a bunch of small rectangles, and those rectangles are going to get mapped onto the R function, R of UV, to the surface. And effectively, this is like a magnification factor of their areas. It is similar to the absolute value of the Jacobian matrix, actually, of the Jacobian determinant, I should say. It's related, and cross products can be computed as determinants. These things are all related. So how would we actually implement this here to find the surface area that we graph with Mathematica? The surface area of this thing. Which, by the way, we should be able to kind of estimate. You know, if this were a disk of radius 3, its area would be 9 pi. It's not a disk of radius 3. It's a curved, warped disk. It goes up really fast over here. So the area is going to be bigger than 9 pi. It's going to be bigger than 28.3. How do you actually find that area? According to that formula that we were just looking at, we need to differentiate the R function with respect to U and with respect to V and take the cross product of the resulting vectors and its magnitude. I think the entire assignment better be done in Mathematica, huh? There's the derivative with respect to V. How do you compute the cross product of these? Oh, it's not Chris, but Cross. Christopher Cross. You ever heard of Christopher Cross? Anybody ever heard of Christopher Cross? Oh, singer from the 1970s. Christopher Cross. That's a real singer. Could I do this? I guess so. And then the magnitude of that. I got to dot that thing with itself. Maybe. Or maybe co-squared. Maybe we can simplify it. Okay, it simplifies somewhat. Okay, what's the magnitude of this vector? Take the square root of that vector dotted with itself. There it is. That's the thing that's got to be integrated. Can Mathematica do it symbolically? Probably not. Probably you have to rely on n integrate to integrate it numerically, meaning behind the scenes it's doing like Simpson's rule or something. N integrate this numerically. U goes from 0 to 2 pi. V goes from 0 to 1. We should get an answer bigger than 28.3. I hope. Okay, 625.6. Okay, is that reasonable? Doesn't seem like it. How high does this thing go? Okay, not that high. Doesn't seem reasonable. Well, okay, wait a minute. Look at the vertical scale. Maybe it is reasonable. And that vertical scale is pretty big. This is definitely not a disk. It's very warped in that one direction. Okay, I'm trusting I did it right. I guess we could look in the back of the book. It's odd. Yang assigned even problems, so I assigned even problems, but maybe I should give you the answers. 14.5, number 3. Okay, they didn't ask you to find the area, so I don't know for sure. All right, let's keep going though with parameterizations. We're not done with number 3. There's a part C and a part D. 2 more parts. Parameterize it over a triangle with vertices 0, 1, 1, 0, and 0, 2. 0, 0, 1, 0, 0, 2. This triangle here. Again, the method is you want to figure out x and y first, and then plug it into the function to find z. That was the method that we just used in part B. We figured out X and Y first in terms of U and V, and then plug those things into the function F to find Z in terms of U and V. And well, this is tricky. What's the equation of this line? The equation of that line is y equals 2 minus 2x, it looks like. Effectively, we want to let x be u and y be v times that formula, v times 2 minus 2x is what we want to do. Why? When v is 0, think about this equation here. When v is 0, you get y equals 0. You get that line right there. When v is 0. When v is the other extreme, 1, you get this line. Same as this one. And in between 0 and 1, v is going to go between 0 and 1, if that wasn't clear. In between 0 and 1, you're going to get lines that are in between. Like if v is 1/2, if v is 1/2, you get the line y equals 1/2 times 2 minus 2x. In other words, y equals 1 minus x. You get this line when v is 1/2. And there are other lines you get for other values of v that are in between. Effectively, as v increases from 0 to 1, you make this triangle by making a bunch of lines like that put together. So that's x and y. Then you figure out z by plugging those things into f in place of x and y. Oh, this x should be a u, sorry. U goes between 0 and 1 as well, but only because of the picture you see that x goes up to 1. Again, the formula for f is 3x squared y. So I got to use that now. Replace x with u, so I get 3u squared, and then y with v times 2 minus 2u. Simplify if you like. Z is going to be 6u squared v minus 6u cubed v. We're not done. That's not the r yet. The r is found now by writing all these quantities x, y, and z in terms of u and v. X is u, y is v times that, which I guess I'll expand to 2v minus 2uv, and z is, well, we simplified here, 6u squared v minus 6u cubed v. This should parameterize the exact same surface, but now over this triangle instead of over the rectangle or the disk. It's the exact same surface, though. The graph of the exact same function. This is the one that did it over the disk. X is u. This one's simpler, really, but y is 2v minus 2u times v. Z is 6u squared times v minus 6u cubed times v. I shouldn't have called these things plot 1 anymore. U goes from 0 to 1, v goes from 0 to 1. Yep, you can see it looks kind of triangular. Let's zoom in closer. It is a piece of the surface, the same surface, over that triangle. What's its area? What's its surface area? We need to differentiate this new one. Let's do the same kind of calculations as we did up here. Copy and paste these things. Yeah, I can copy and paste all this and just make adjustments. There's re-enter these things. Here's the derivative with respect to u. Here's the derivative with respect to v. These things are simpler. Disks give the most complicated equations, it seems. The cross product is this. Square root of that thing dotted with itself is going to be the magnitude. Right? Square root of a vector dotted with itself is its magnitude. That's what we got to integrate. U goes from 0 to 1. V goes from 0 to 1. It feels like we should get closer to the area of this triangle here. The area of that triangle is 1. 1/2 base times height. Hopefully we don't get an answer too much different than 1. A little bit bigger. Yeah, okay. The graph's more interesting than I thought at first. From far away, you couldn't see it very well. But there it's got some curviness to it. I zoomed in closer. Let's go even closer. Okay, so then we found the surface area. Part D, between the x-axis and the graph of that function. Let me actually change part D. Let's make it a little bit more interesting, maybe. New part D. Instead of between the graphs that were indicated, let's pick different graphs. Let me parameterize it between two different parabolas. Y equals x squared. And maybe another parabola going like this. And well, how can I pick this to make this a nice number? Y equals 4 minus x, or maybe 8 minus x squared. Where are those going to intersect? 8 minus x squared equals x squared means 2x squared equals 4, or 8, excuse me. So x squared is 4, x is plus or minus 2. So they intersect at 2 and negative 2. I'm interested in parameterizing the surface over this region. To be consistent with the book's notation, let's call this function g1 of x and this function g2 of x. What you want to do to parameterize the surface is you want to let u equal x going between 0, negative 2 and 2. Well, okay, should write it the other way around. X equal u goes between negative 2 and 2. And then let y be g1 of x plus g1 of u, excuse me, plus v times the in parentheses g2 of u minus g1 of u. What's going on there? When v is 0, this becomes y equals g1 of u, which is g1 of x. You get the lower parabola. When v is 1, you get y equals, plug in 1 here, the g1 of u's will cancel. You get y equals g2 of u, which is g2 of x. So effectively, by doing this, what you're doing is v goes between 0 and 1. Oh, sorry, this should have been a u here as well. As v goes between 0 and 1, is you are parameterizing with parabolas. You're getting intermediate parabolas. And actually, when v is 1/2, you get a horizontal line, I believe. And then you plug those things into the function to get z. So z is f of u comma g1 of u plus v times g2 of u minus g1 of u. And for our example, that's going to be f of, oops, that's not right. There's an extra v in here. That's got to be the z, no, oh, sorry. That is y. This is x. This thing is y. Then you plug those things. I'm getting confused. Yes, this is correct. I still haven't figured out r yet, though. R of uv is u comma this thing comma this thing here. But that's what you would plug into F to ultimately find R, and you could find the surface area in the same kind of way. Yeah, kind of nasty. But for the purposes of understanding surfaces and surface integrals, ultimately necessary. Why does this work? I explained why intuitively by talking about what happens when V is 0 and when V is 1. You could also think about intermediate values of V. You would get graphs like I drew in red here. Intermediate parabolas for the most part, one of which is probably a horizontal line, a degenerate parabola. Simplest to let X be U, Y be this thing, and then plug those things into F to find Z, and then create your R function that way. By the way, the derivative of R with respect to U or with respect to V can be thought of in terms of tangent vectors. Now not to a curve, but to the surface itself. Those vectors end up being tangent, just like derivatives, the derivative of R prime of T was tangent to the curve for a parametric curve.